Welcome back to the deep dive. Today we're taking a bit of a shortcut
Hmm.
into the incredibly tiny yet monumentally complex world of microchip design. We're talking very large-scale integration, VLSI, and the big question we're tackling is how do engineers actually pack billions, literally billions of transistors onto one tiny chip without, well, everything just going completely wrong?
That really is the core challenge, isn't it? VLSI, it's exactly that process, integrating millions, sometimes billions, of these tiny switches onto a single piece of silicon.
Right.
But it's not just about making things smaller. It's a constant fight against these invisible forces, these subtle effects that can totally mess up how the chip works or if it works at all. Reliability is key.
Okay, let's unpack that. These invisible forces. Our mission today really is to give you a real feel for what's happening down there at that microscopic level,
Yeah.
and maybe reveal some of the, frankly, ingenious ways engineers tackle these issues to make our digital world possible. And this is where it gets really interesting. Just imagine, a tiny antenna inside your chip, an antenna that could actually destroy it. Sounds a bit like science fiction, doesn't it?
It does, but it's very real. It's called the antenna effect.
Yeah.
You see, during manufacturing, there's a step using plasma etching.
Okay.
And during that process, bits of metal or polysilicon on the chip, they can act like tiny antennas and accumulate electrical charge, like static electricity, but very concentrated.
Hmm.
And if that charge builds up too much on a large piece of metal or poly acting as the antenna, it needs somewhere to go. It discharges, zap, right through the gate oxide.
The gate oxide. That's like
Yeah.
the super important insulating layer in a transistor.
Exactly. It's incredibly thin and delicate. A discharge like that punches right through it, destroying the transistor. So yeah, a large conductive area literally becomes an antenna collecting destructive charge.
Wow. A tiny self-destructing lightning rod built right in. Is this still a major headache or is it mostly solved now?
Oh, it's definitely still a headache, a persistent one. Designers have developed really sophisticated antenna rules for layout and tricks like adding little sacrificial diodes or reverse biasing junctions nearby to sort of bleed off the charge safely.
I see.
But every time we shrink the transistors and wires further for the next generation of chips, these structures become even more sensitive. So it's a constant balancing act.
Okay, so that's like immediate electrical danger, zap, gone. But what about something maybe a bit more subtle? Like what happens if a chip just can't make up its mind fast enough, a sort of digital indecision?
Ha! Digital indecision. That's a good way to put it. That phenomenon is called metastability. Think about a flip-flop that's your basic digital memory bit, storing a 0 or a 1.
Right, the fundamental building block.
Well, it needs a tiny amount of time to reliably capture the input signal and decide if it's a 0 or a 1. There's this critical window, sometimes called the aperture time. If the input signal changes right during that tiny, tiny window,
Uh-oh.
yeah, the flip-flop can get confused. It can enter this weird in-between state, not quite high, not quite low. That's the metastable state. It's like it's balanced on a knife edge.
So it hangs there, undecided. What happens then? Does it stay stuck?
It won't stay stuck forever. It will eventually resolve to a stable 0 or 1. But the problem is, how long does it take? If it takes too long, or if that unstable signal propagates through the system before it resolves.
Chaos. Corrupted data system crashes.
Exactly.
Yeah.
Total chaos, potentially. So engineers work really hard to prevent this. They use very careful clock synchronization design and sometimes special circuits called synchronizers or resynchronizers.
Like a buffer zone.
Sort of, yeah. These circuits basically give the signal an extra clock cycle or two to settle down and force a clear decision, even if it introduces a tiny controlled delay. It ensures reliability.
Okay, makes sense. Fighting indecision with careful timing. Now, thinking about long-term effects, like wear and tear, can high currents actually, like, erode the tiny wires inside a chip over time?
Yes, absolutely. That effect is known as electromigration. It's a major wear-out mechanism. You have these incredibly thin metal interconnects, the wires linking everything.
Yeah, unimaginably thin.
Right. And when you push a high density of electrical current through them, the moving electrons are constantly bumping into the metal atoms of the wire itself.
Like a constant tiny bombardment.
Precisely. And over time, this momentum transfer can actually nudge the metal atoms, causing them to drift, to physically move from their original positions.
So the wire gets thinner in some places, or voids form?
Exactly. Voids can form, or the metal can pile up elsewhere, causing shorts. Eventually, the wire can thin out so much it breaks, creating an open circuit. Or it might short to a neighbor. Either way, failure.
So that's potentially why an old phone or computer might start getting glitchy or just die after years of heavy use. It's the wires degrading.
That's definitely one of the major reasons for age-related failure, yes. Electromigration. Designers fight it by making wires wider in high-current paths, using specific metal alloys that are more robust, like copper with small additives, and carefully managing current densities everywhere. It's all about predicting and extending that lifespan.
Okay, wow. And speaking of signals traveling down these wires, what if they get noisy, like interference between adjacent wires? Kind of like getting crosstalk on an old phone line, but inside the chip?
That's a perfect analogy. It's called the crosstalk effect. When the logic state changes rapidly on one wire, one net, the changing electric field can induce an unwanted voltage spike, noise, onto a neighboring net.
And that could flip a bit or mess up timing.
It absolutely can. It can cause errors, glitches. So managing this is part of a broader concern we call signal integrity. That's the overall quality measure. How well does a signal transmit information reliably without getting distorted or corrupted by noise, crosstalk, reflections, things like that?
Right. Keeping the signal clean and clear.
Exactly. And one very common technique specifically to combat crosstalk is net shielding.
Shielding, like building little walls between the wires.
Pretty much, you intentionally run ground wires, or sometimes power wires, parallel and close to sensitive signal wires. These shield wires act like barriers, absorbing or diverting the interfering electric fields from the noisy neighbor.
So like putting up little electrical fences for data privacy?
That's a great way to think about it. It isolates the sensitive signal from the noise source.
Okay, so let's pull this together. We've touched on these tiny, almost sci-fi sounding problems, internal antennas causing shorts, flip-flops getting stuck undecided, wires literally eroding away from electron bombardment, and signals interfering with each other.
Yeah, it's quite a list.
It really makes you appreciate well, the incredible engineering that goes into every single chip, making sure all this doesn't happen, or at least happens very rarely, so our devices actually work.
Absolutely. What's really fascinating, I think, is that every single one of these concepts, managing charge buildup, ensuring precise timing, preventing physical degradation, maintaining signal purity, every single one is critical. You miss one, the whole thing might fail. It really highlights the unseen complexity humming away inside our electronics.
It truly does. So next time you pick up your phone or use your computer, maybe take a second to think about these invisible battles being fought constantly at the nanoscale and the incredible ingenuity of the engineers solving these incredibly complex problems. It makes you wonder what other hidden complexities are humming away inside the technology we use every single day.